Okay, so in the previous episode, we discussed the first solution concept called Nash equilibrium, and so we want to show the existence of the Nash equilibrium. So we use a theorem called Kakutani's fixed point theorem. Okay, so it is one of the famous fixed point theorem, and we use that to show the existence of the Nash equilibrium. Okay, so now let's first define or first introduce some notations for us to define the to show the statement for this theorem. Okay. All right. So let's say the X is a subset of a real in n dimension, okay, Rn, and the set X is it is compact, okay, if X is closed and bounded, okay. Okay, so this is essentially the requirement for the compactness. Okay, so X has to be both closed and bounded to be compact. Okay, so let's say in the two-dimensional space of real numbers, let's give some examples of the compact set and some counterexamples. Okay. Okay. Let's say a set X. Okay. Within this range, this little shape here is a compact set. Okay. Okay. But if this set doesn't include the boundaries, okay, it is called an open set, right? So it's not closed. Okay. So if it's something without boundaries and is not closed, so in this case, this is not compact, right? Okay, and for another example, if it's not bounded, so it means that it's not limited, right? So it will look like something like this. Okay, maybe it has some boundary, but it goes to the infinity here. Okay, all the way to the up and right. Okay, so it's not bounded, so there's no no limit, or we just use the unbounded, right? So that's the rigorous term. Okay, so and we also introduce the convexity of a set. So X is called a convex set if for any 2 points, okay, X and Y in set X, okay, and for all real numbers alpha between 0 and 1, we have any linear combination or any convex combination of X and Y given alpha and Y minus alpha as their weights. Okay, so the weighted sum is still in the set X, and then we call this X is a convex set, okay, for any X and Y and any alpha. So a set looks like this would be convex, okay, X, Y. But if a set which looks like if it has some cavity here, okay, then the connection, some point in the middle would be outside of this set X, right? So this would not be a convex set. Okay. All right. So that's pretty much everything that we need to define to give the statement for the Kakutani's fixed point theorem. So Kakutani's fixed point theorem. So essentially, it's saying that so set X in Rn, okay, is a compact and convex set. Okay. Is a compact and convex set. Okay. And we let F to be a correspondence that we mentioned previously. So it is not a function, right? So it's a correspondence. So it's a map from X to X. Okay. So the so X is both the origin and the destination of this map, right? And the image space. Okay. So this would be a correspondence such that, so we have two requirements for that, right? So the first is that so for all elements X in the set X, so this correspondence Fx would be a non-empty and convex, right? So it's non-empty and convex. So that would be the first requirement for this statement. And the second is that so the graph of F is closed. Okay. So it means that the graph of X, so essentially the graph of the correspondence, right? So the graph of F is closed. So it means that it's including the boundaries, right? So that's the meaning of closed. Okay, so more rigorously, what we mean is that for all the sequences okay, let's say xn and yn such that yn is an element of the correspondence F with input xn, right? So that those are the elements in the sequences, right? Given for all n's, right? And we have that xn converges to x and yn converges to y, okay, for those two sequences. And we have y in the limit would be an element of the F correspondence with input x in the limit. Okay, so that would be the definition of the closeness of this graph of the correspondence F, right? Okay, so those two are the requirements, and then the statement would be that there exists x star, okay, within X, such that x star would be an element of F correspondence with input x star itself, okay? So, and intuitively we can see that this input of the correspondence F is x star, and the output x star is in this correspondence and is still itself again, right? So, and namely this is the meaning, and that's why we call this as the fixed point theorem, right? So it's sort of a fixed. So what we are inputting is actually the output of this correspondence, right? So it's within the set of the correspondence of the output of that F, right? So that's the meaning of the correspondence, meaning of the statement of the Kakutanis fixed point theorem. Okay? And later we'll use that to show the existence of the Nash equilibrium. Okay. All right, so now let's take a look at the example and to briefly illustrate the idea of the fixed point theorem. Okay, so let's suppose f, this correspondence, would be a map from unit interval 0, 1 to 0, 1. Okay, so with this definition of f, so this, we already guaranteed that this f would be compact first, right? So it's compact and it is convex. Okay. All right, so now let's use a graph to plot this example here. So in the two-dimensional Euclidean space, okay, R2. So this will be the 0 and 1 here, 0 and 1, okay. All right. So we connect this 45-degree line, all right, and we change a color. Okay, let's say a correspondence is somewhere in between of those two blue lines, okay. And we can see that the blue lines have a lot of intersections with this black line here, the 45-degree line, right? So it means that there are a lot of fixed points in this case, right? But actually, the Kakutani's fixed point theorem just wants to show at least there exists at least one fixed point, right? So here we have a lot of those. Okay. Of course, it has at least one, right? Because it has a lot of in this example. Okay, so so intuitively, it means that the existence of the fixed point, okay, so what does the existence of the fixed point mean, right? So it means that the 45-degree line at least attaches or intersects or whatever, right? So it gets to the or attaches the f, right? The correspondence at least once, right? Correspondence at least once. Okay. So that's the meaning, or that's the interpretation of the Kakutani's fixed point theory. Okay. So it means that no matter what does the f look like, right? So no matter f1, f2, or any f is like looks like. So f has to attach the 45-degree line at least once, right? Okay, so and this has to be true if the requirements for the set x and the graph of the f are holding in the as we mentioned previously, right? So we cannot just give some counterexamples unless we break some or we violate some of those conditions, right? So now let's just make some breaks, or we just violate some conditions and see how would the results change, and in this case, and then we'll see that if the conditions are violated, then actually those fixed points may not exist at least once, right? At least one. Okay, so if the conditions are violated, okay. All right, so the very first condition that we're going to violate is that the non-empty assumption for the correspondence f, okay. So if f is not non-empty, okay, so it means that f might not be empty, okay, at some point. So let's say if f1 in the previous example, f1 would be just the empty set, okay. So in this case, it means that we have a circle here, right? And so it's empty here. Oh, actually it's not there, right? So it should be empty in the F's, right? Okay, so if F1 is empty, then in this case, this might not be true. So it means that there may not exist at least one fixed point. So to show that, we can draw another picture to show the intuition of that. So let's say this is from 0 to 1. Again, the same example. So this is the 45-degree line. Okay, so to have a very counter example of that, so we need that correspondence to be pretty special, such that it goes somewhere to here, okay, to this corner, and the lower bound goes here. Okay, if the limit, if f1 is an empty set, okay, so if it returns an empty set, then we have a empty circle here, right? So in this case, the blue lines has no attachment, or it doesn't attach the 45-degree line and at least once, right? So there's no intersection of those two lines. Okay, so that's the first situation that we violate the conditions. Okay, now let's go to the second one. So if, let's say, if X is not compact, okay, so namely, first, okay, X is not closed. Okay, so if X is not closed, then let's say X is from 0 included, but to 1 not included. Okay, so it's open on the right hand, or on the right side. Okay, all right, so again, have the little picture here from 0 to 1, okay, the 45-degree line. Okay, so we have a empty circle here, right? So it's not defined here. So X doesn't include this one here on 1. So it means that this blue line, or this F, could just not attach, or just not intersect with the 45-degree line once, right? So there could not be a fixed point, okay, using the same example that we mentioned. Okay, all right, so that's this the first case. So the other case would be that X is not bounded, right? Okay, so if X is not bounded, then let's suppose X to be something from 0 to infinity, right? So what does it mean in this case? It would be something like this. So this is the 45-degree line, okay, and it goes all the way up there, right? So there's no end for those graphs. So we can just draw those blue lines to the infinity, right? All the way up there, okay? So in this case, we can see that the blue lines do not have to intersect with the 45-degree line, right? So they can just all go up there into the infinity. Okay, good. So that's the second condition that we're going to violate. And the third one is the convexity, right? So if X is not convex, okay, so let's say X is something, some set with a union from 0 to a quarter, okay, and union to let's say 3/4 to 1, okay. Then we can consider a correspondence F, okay, such that Fx would be something like this. So we can draw the picture first and then choose a proper f to have no fixed point for us, right? So this is 1, this is 1, 0. Okay, this is the 45-degree line. All right, so this is 1/2, quarter, 3/4. All right, so let's say if f is such that in those two corners, okay, this is quarter, 3/4. Okay. If f is within this corner or within this corner, okay, so it means that if x is in 0 to 1/4, then fx is 3/4 to 1. Okay. Otherwise, if x is within 3/4 to 1, then fx is in 0 to 1/4. Okay. All right, so we can see that the correspondence are within those two corners in the shaded areas, and obviously there is no cross point with the correspondence to the 45-degree line, right? So it means that there's no fixed point in this case. Okay. All right, so that's pretty much for the conditions for the set x. Then we also have some conditions to violate for the f, right, for the correspondence. So now we look at f's convexity. Okay, that is something that we're going to violate. So if for some x in the set x, so the correspondence fx is not convex. Okay. So let's say x is between 0 and 1. All right. So the picture looks like this. 0 and 1 again. Right. However, let's suppose f of a half is something like this. Okay, it's a union of two sets from 0 to 1/4 and union to 3/4 to 1. Okay, so at 1/2 this becomes like this, right? And obviously in this case we know from the previous example, and there's no fixed point in this case, right? No intersection with the 45-degree line. Okay, so the last condition that we're going to violate is the closeness of the graph, right? So if the graph of f is not closed, right? So we still have x from 0 to 1, same picture. Okay. And there may not exist the fixed point again, right? So rigorously, let's say if x, let x n, the sequence to be 1 minus 1 over n, where n is a positive integer, right? So the limit of xn as n goes to infinity, this will be 1, right? And so yn is in the correspondence of fxn, okay, in the sequences, and so the limit of yn as n goes to infinity will be 1 as well. All right. Okay, so let's write in the other direction and just put 1 to here. Okay, so that actually is not an element of the f of limit xn as n goes to infinity, which equals to the set with one element of 0, right? So, and we can see from this picture, so it means that limit of yn is 1 here, right? But we have this as an empty circle, right? Because the limit of xn with this correspondence, the output is just 0 here, okay? Because of this sequence. So we have, because of the correspondence here, because of the graph of f is not closed, okay? All right, so then we can see that those conditions are all necessary, right? And then we, later, if we have opportunities, then we can show that the actually the proof of the Kakutani's fixed point theorem itself, right? But here, the purpose of showing this Kakutani's fixed point theorem is to use that to prove the existence of Nash equilibrium, right? Okay, and later we'll use new episodes to show to use this to prove the existence of Nash equilibrium. But in short, right? So briefly, what we want to show is that we know that the best response correspondence is sort of an analog to the to this correspondence f, right? So if we can let the best response correspondence to have some nice properties that we have here for the Kakutani's fixed point theorem, then we can actually show that the existence of Nash equilibrium, such that as what we are doing here, to show that the existence of the fixed point, right, from the Kakutani's fixed point theorem. Okay, so rigorously, what we're going to do is that we want to show the so later we will show the existence of Nash equilibrium by using the Kakutani's fixed point theorem, and later we will see that the action profile or the outcome A, okay, with an typical element A star. So this in equilibrium, so this would be an analog to the X set X, right, that we showed here in this episode, such that, so we want to show the existence of that, right, such that the A star, right, would be in the set of the best response correspondence with input of the A star itself, right? So that's what we did in the Kakutani's fixed point theorem, and those are the analogs to the Nash equilibrium. Okay, so later we'll in detail discuss the proof of this. Okay. All right.